off.
But
yeah, my energy levels are pretty good. So, and Freddie is also feeling well, I think. So, yeah, I think I'll be able to go back in person by Thursday.
Good.
Oh, wow. And
Did Freddie's daughter get sick?
I don't know. I hope not. Yeah. So I hope you stay well, Jeff, before your flight.
Thanks. I've been somewhat quarantining, and I think at this point it's 4 days. So
let's see. We're being asked.
Well, we better send a message to Jack and say no. There's no sound. Oh, right. Okay. Thanks. There we are. Okay. Now we're mic.
Others who work engineering aerosol people have documented that when you're talking and talking loudly, you're emitting 100 to if you were just breathing. And I tested useless, but if you're positive, it might tell you that. So hopefully there will be no transmission of COVID in this room. And it would be ironic if there were, since I spent the last 2.5 years trying to prevent COVID transmission. Okay, as you know, I'm going to be talking about modeling the transition to turbulence. And the focus is on modeling. And the things I'm going to tell you about involve techniques from partial differential equations, stochastic processes, quantum field theory, renormalization group, plus something else, a secret ingredient. What's the secret ingredient? Anybody want to guess? Experiment, yes, but that's not a model.
Machine learning?
No. But I think it has a part to play, though. And we can hold that thought. We can talk about it in the discussion later. Yeah, somebody else had a comment? Biology. Well, that's not a modeling technique. The modeling technique is creativity, inspired interdisciplinary creativity, because you can't, theoretical physics is not about the mathematics, it's about the guesses that you make, the intuitions that you have, and then using mathematics to try and tie it all together. And this problem that I'm going to be talking about is one that's been around for well over 150 years. And even now, we don't understand it completely, but we've made a lot of progress in the last decade or so. And so that's what I'll tell you about. Okay, so we're going to start off, and these talks are going to be partially on the view graphs, on the PowerPoint, partially Blackboard. Each of these topics here is a graduate course at a university. So I'm only going to be able to aspire to give you the ideas, the rudiments, the flavor of what we do. I have provided about 50 journal articles, which amplify on a lot of the techniques that I'm going to invoke, the results I'm going to use. And I'll be happy to answer questions about which articles to read in the Journal Club channel on Slack. So don't DM me for those things, because everybody else will want to see the answer to the questions. But there's a lot of materials that I've put there for you and to help you, if those of you who want to dig deeper can do so. So we're going to talk about, first of all, why do we care about transitional turbulence? Because, hey, we're physicists, right? So the only thing that matters is scaling and multifractal exponents and stuff like this. And that's all fully developed turbulence. And we want to understand all of that. We want to understand the dissipative anomaly, the normalization group, and so on. So that's not cool, transition turbulence. That's low Reynolds number, usually. So why do we care about it? Well, I'm going to tell you why I care about it. And then we're going to, I'll show you some observations and experiments, observations that I took a few days ago, And then we'll talk about, we'll have to take our first Blackboard break, intermission, and we will talk in detail about how, when you have the coexistence of laminar flow and turbulence flow, how the boundary between them moves. And what I'm going to show you is this is going to be a high Reynolds number. And I'm going to show you that we can understand that in a beautiful way that goes back to ideas of Kolmogorov in 1941, but also Kolmogorov 1942, which many people don't know exists. And also we will do a renormalization group calculation today. I'm going to do it in a sneaky heuristic way. So if you don't know what renormalization group is or how it works, it won't matter, okay? Then we're going to talk about the types of transitions to turbulence that there can be. And I'm going to talk about supercritical and subcritical transitions, which in dynamical systems language is roughly the equivalent of first order phase transition to second order phase transition, those two types of things. And we'll talk about them. I'll show you how to do an honest calculation looking at linear stability analysis. And what we'll use is we'll look at a model of convection, and we'll try to understand the stability of the laminar state, or a laminar state, in turbulent convection. And we'll see how it all goes wrong. And in fact, we'll talk about Heisenberg's PhD thesis, which, as you know, was not on quantum mechanics. It was on the transition to turbulence. And we'll talk about why it was right, but irrelevant. And maybe he knew that, but and maybe that's why he switched to inventing quantum mechanics rather than carrying on with this problem. However, if you read his thesis, it's very interesting because in it he discovers, he uses mathematical techniques that he invented to study stability of laminar flow, particular laminar flow. And some of the techniques he used later came up in quantum mechanics, in WKB theory and so on. So it wasn't all wasted. Okay, then we will get on to the first topic of pipe flow turbulence, which will be puffs, and we'll probably get to that tomorrow. So let me put this up here for now, and let me go to the next slide. Okay, so let's start with propaganda. So we've all read Feynman lectures on physics, and if you read volume 2, you will find, and after he discusses electromagnetism, there's a few chapters on fluid mechanics, and he derives the Navier-Stokes equations. And this is what he says. He says, we've written the equations of water flow. We find a set of concepts and approximations to use to discuss the solutions: vortex streets, turbulent wakes, boundary layers. Hopefully you've heard about some of those things at this school. When we have similar equations in a less familiar situation, and one for which we cannot yet experiment, we try to solve the equations in a primitive, halting, and confused way to try to determine what new qualitative features may come out or what new qualitative forms are a consequence of the equations. Now, I've underlined and put in italics, and made in boldface and in red, the word qualitative, okay? Feynman is famous for many things, and one of them is that he was the world's best calculator. He got a Nobel Prize for calculating, showing how you can do renormalization in quantum electrodynamics. It's our most successful theory. You can do measurements, the calculations to 10 significant figures. It agrees perfectly, okay? But here Feynman is upset because he can't even understand the qualitative content of equations. And what he says is the next great era of awakening of human intellect may well produce a method of understanding the qualitative content of equations. Today we cannot see that the water flow equations contain such things as the Barber pole structure of turbulence that one sees between rotating cylinders. That's Taylor-Coët flow. I'm sure you've been exposed to that. So that's really, really interesting, because when you ask what is the qualitative behavior of matter, that's the domain of statistical mechanics. The only thing that you care about in statistical mechanics, your first approximation, is what is the phase diagram of the matter that I'm talking about? And what Feynman is saying, translated into my language as a statistical mechanician, is that we should understand the phase diagram, and if there is, any transitions and universality and scaling laws of turbulence using statistical mechanics. And I'm going to show you that we can do this. I'm going to tell you about new predictions that we've made using statistical mechanics that can't be made by any other way that I know of. And those predictions have been tested experimentally, and they work. And I'm mostly going to talk about transitional flows. In the third lecture, when I talk about open problems, I'll try to say a little bit about fluctuation, dissipation relations. Okay, just a quick sort of hand-waving way in case you're thinking, wait, I'm here to understand fluid mechanics. Do I need to know the Navier-Stokes equations? Well, maybe. If I have a bunch of particles bouncing around in a box, and you go and simulate that on a computer, which you can all do, you will find very quickly that you can, measure the pressure, you can measure the equation of state, you can see that it agrees with what you get using the arguments that you were taught in statistical mechanics. That's a finite number of particles. Now let's go to an infinite number of particles. An infinite number of particles, the Newton's equations of motion, look like this. This is just the acceleration, this is the driving force, and I've added here the friction, which is this term over here, and the incompressibility. And what we have then is the deterministic classical mechanics of an infinite number of particles in the box. What we really have is a coarse-grained picture, a filtered picture of the velocities on microscopic scales, coarse-grained up to a scale that we then feel comfortable writing things down as a continuum partial differential equation, like so. Now, because a finite number of particles ended up giving you statistical mechanics, maybe you won't be so shocked that an infinite number of particles also gives you statistical mechanics. But of course, to demonstrate that is exceedingly hard and it is a topic of open research. But in any case, that should give you a feeling for why one might think this would be true. Now, when we talk about statistical mechanics, the flows I'm going to be showing you today and talking about are mostly open flows. So they're in a non-equilibrium steady state. Stuff is coming in, stuff is going out. This is not, canonical ensemble equilibrium Stan Mech that you saw in your graduate Stan Mech classes. Okay, so we're here in more detail is what I'm going to talk about. So this is mostly today's lecture. Why are we interested in transitional turbulence? Propagation of fronts, supercritical and subcritical transitions. The stuff that's really the new stuff starts off probably a little bit today and a bit next time, and mostly next time. We're going to see that there's little patches of turbulence that were discovered by Reynolds in 1883. And those little patches of turbulence we call puffs. We call them flashes. We're going to see that those things, as you increase the Reynolds number in the pipe, get created by, say, a disturbance, and then gradually diffuse or die away. And how they die away is extremely interesting. And the lifetime of these things is very counterintuitive. And we're going to see that we need another technique to add to these. I knew I forgot one. Extreme value statistics. We're going to need other techniques to understand the behavior that is seen in experiment. I'm going to talk about some models of puffs, mostly our own work, which uses, well, you'll see when we get into it. I'm going to talk about directed percolation. I'm going to talk about directed percolation because the punchline of all of this is that the laminar turbulence transition in pipes is a non-equilibrium phase transition in the universality class of directed percolation. And we can predict the exponents, we can predict the universal scaling functions, we can measure them in experiments in the last couple of years, and it all fits exactly. Okay, it's amazing. You just start in Navier-Stokes equations, either fluid or in a computer. There's no statistical mechanics, no temperature, nothing else. And yet when you go and look at the critical point, the transition to turbulence, you see this remarkable non-equilibrium phase transition. At the end of tomorrow's talk, we will talk about not only the experimental tests, but new work that has not yet even been submitted for publication. It's about to be on the interactions between parts. Okay, then the third talk is mostly going to be new work on slugs. That is the spreading of turbulence. That's the propagation of a laminar turbulent interface, but now at low Reynolds numbers, not at high Reynolds numbers. And that was work that was done in collaboration with Xiaoying Wang, who is sitting here and helped with some of the slides and was a great collaborator on this work. And this work just came out in Physical Review Letters in the print edition today, I think. And then at the end, I'll talk about the things that we don't understand, and I'll be happy to talk about the questions. Okay, so transitional turbulence, who cares? So this is what happened to me a few days ago when I was driving across Arizona. I'm going to show you a movie, and I want you to ask yourself the question as you watch this movie. Where is the turbulence in this movie? So I'm driving along a street in Arizona, and as we start to see sand drifting in patches. And then as I get a bit further on, the sand density starts to increase, and I start to get a little bit worried. Sand density increases, and and the wind speed, you can see the trees are growing, and then all of a sudden it gets really terrible, and you see just massive sandstorm of wind and dust, and it's really, really terrible. And so the question I want you to ask yourselves is, where is the turbulence in this sequence of events? Okay, which part of this is turbulent? Now, what we saw in the movie was this. We saw strong wind speeds, and we saw blowing sand. So you might say to yourself, well, it's obvious, right? There's a strong wind blowing, it picks up the sand, and so that's why we see strong winds and we see blowing sand. So you might say, well, it's obvious, right? The strong wind caused the sand to fly. But maybe that's not true. Maybe the flying sand caused the strong wind, right? And why could that be? Well, why people care about turbulence is because it messes things up. If you want to fly an airplane or send gas or oil through a pipeline, the frictional drag is much higher when there is turbulence. And that means you have to spend more energy to move stuff around, move fluids around. So that's bad. So you want to try to reduce the drag. You want to try to reduce the rate at which you're using petrol in your car and so on. And what people discovered was you start putting anything into a turbulent fluid and it suppresses the drag. It suppresses the turbulence. So what's happening here is that sand can suppress turbulence. Turbulent fluctuations can scoop up sand from the ground. The sand gets into the flow. It suppresses the turbulence, and it suppresses it because turbulent kinetic energy is used to suspend the grains. It interferes with the energy flow, the very subtle energy flow that gives rise to the Kolmogorov spectrum and other things in turbulence. And so in some sense, it causes the turbulence, roughly speaking, to become less turbulent, to be more laminar, if you will. I'm going to show you in a few minutes that the speed of a laminar flow is much faster than the speed of turbulence. And so the wind now is going faster. And because it's going faster, it can pick up more sand. And so you get a feedback loop. And that same feedback loop is what I think is also important in the generation of tornadoes. Because in tornadoes or dust devils, you always have a suspension, and you have the following facts. You have a very localized tornado, and you have very high wind speeds, and you have suspensions. And to this day, even though we have a very good understanding of the thermodynamics of tornado genesis, we don't have a very good understanding of the rate at which tornadoes form and the possible role of turbulent drag suppression in tornado genesis. And I think that's a very interesting research problem. Now, I want to, oh, yes, question.
So I want to understand that part that sand suppresses the
Yes,
So if instead of sand, we had mud,
yeah,
so that the wind couldn't pick it up.
that
we-
wouldn't. That wouldn't suppress it.
Okay, so we would get a.
You need
more
to,
sand
so the question is, if you had mud rather than sand, would that work? And the answer is no, as far as I know, because you have to have the little particles suspended in the flow. What they do is they add inertia to the flow by their mass. So that increases the turbulence, but then they take up turbulent energy because you have to levitate them. And so those things compete. And it's actually very, very complex interplay between those things. I have oversimplified it massively for this purpose, but
So I think so they both suppress turbulence and also add to the.
it depends on the size of the particles. So there's people who spend their entire career studying this. It's a really important topic. So I'm somewhat oversimplifying. Did I answer your question?
Yes, thank you.
Good. Okay. Let's have a look at what happens when you do this in a laboratory. So Nicorazzi in 1933 did my favorite experiment, or my second favorite experiment in turbulence. My favorite experiment was done by Björn Hoff, my collaborator and friend, but the second favorite one was the one done by Nicorazzi in 1933. And what he did was he took a pipe and then he got sand grains, carefully shifted them so they were all exactly the same size. And then he glued them to the sides of the pipe, like you can see here. And then he measured the pressure drop per unit length, normalized by the kinetic energy density of the mean flow, rho u squared. That was a thing called the friction factor. So you might think, well, what's the friction going to look like? Well, let's think about this in our heads. Normally, you would think if I move through a fluid, I experience a drag force proportional to my speed. So similarly, if I move the fluid through a pipe, I should experience a drag force proportional to the speed. So that would say that the friction factor is proportional to u, or the pressure drop is, but it's normalized by rho u squared. So that would say that if I had a laminar flow, the friction factor would scale as 1 over the speed, the mean speed, which would translate into 1 over the Reynolds number. Okay, so that's what you would expect. But let's have a look at the data. So here's the data. This is the log of the friction factor against the log of the Reynolds number. Nicorazzi did this for pipes of different radius compared to the pipe diameter. That's the number plotted over here. And of course, the smoother pipes have smaller friction factor. The larger pipes have larger friction factor. And what you can see here, this slope here is exactly 1 over Reynolds number, just like we guessed in our thought experiment. But then you can see something weird happening. There's a thing called a drag crisis, which happens around here. This is the transition to turbulence. Most of what I'll talk about for the next couple of days is about this. And then you can see that this weird non-monotonic behavior, like so. And what you can see is, as I go to large Reynolds number, the friction factor becomes independent of Reynolds number. That's really weird, right? For laminar flow, you would think that the friction factor would scale with the Reynolds number in some way, but as you go to large Reynolds numbers, it becomes independent of the Reynolds number. Okay, that's amazing. Why? And it only depends on the roughness. And in fact, I'll show you at the end of these lectures, if I have time, that we can understand this behavior as a critical phenomenon. The other thing that you can see here is that as you go down these sequence of curves, you can see that the curves peel off from this line that's drawn here. This line has a slope of Reynolds to the -1/4. It's known as the Blasius scaling. And Prantl, within whose lab Nicorazzi worked, had a theory for the shape of these curves for a smooth pipe. These data don't really agree with that theory at all. And this is a source of active research and controversy in the turbulence field at the moment. Björn Hoff has done nice experiments to really do this thing, to measure these data as accurately as possible. Okay, so this behavior here, my colleague and collaborator, friend, Greg Iyenk from Johns Hopkins University, likes to call this a strong anomaly, and he likes to call this a weak anomaly. How does this power law change? And the answer, this part here, this is the most interesting thing here, I suppose. It comes about because the friction, the pressure drop per unit length, is proportional not to the velocity, but to the velocity squared. Okay, and because it's proportional to velocity squared, when you normalize by the velocity squared, you get a friction factor that's independent of Reynolds number. Okay, pop-up quiz. Who was the first person to realize that the friction of the pressure drop per unit length scaled as the velocity squared, not as the velocity? Heisenberg, no. What? Bernoulli, well, no, too late. Earlier than that, I think. But good guess. Pardon? I'm sorry, I can't hear you. Newton. Yes, you're right. Newton realized this. Newton understood this. Then it was and how he got this idea is just amazing. I'm not going to talk about this. The next person who understood this was Chézy, who was a French engineer in the 1700s, trying to dig sewage pipes and drainage canals in Paris. And then, of course, Kolmogorov understood this most famously in 1941. But everything that Kolmogorov studied and came up with could have been done by Newton, but wasn't. Okay, so now Blackboard interlude. Let's try to do an honest calculation or two. So I want to show you a little bit about the consequences of this drag. So what we're going to talk about is drag, and the first question we're going to talk about is the speed of a river. So the question we're going to ask ourselves is, how fast does a river flow? And the answer is a kind of surprising one. So let's draw a river flowing. So it starts off in the Colorado mountains, some height above sea level. It goes down to sea level over here. There's water is always blue. So here is the river. Water has a depth, which I'm going to call D. It's flowing with some mean speed U like this. It goes over a distance L in this case, and there's a small angle theta over here. And we can estimate what's roughly orders of magnitude. So L might be 10 to the 6 meters. G might be, say, 10 meters. H is about 10 squared meters. Theta is going to be about 10 to the minus 4. And G, gravitational acceleration, is about 10 meters per second. Okay, so now we can do a few estimates that even a tenured professor can manage to do. So the first thing you might say is, well, it's pretty obvious. We know how to solve this problem. We learned this on our mother's knee. All you have to do is work out what is the potential energy of the water here, and then translate that into kinetic energy over here. So let's go and work out what happens when we do that. So method number one. Energy conservation. So basically what we're going to say is, we have fluid, kinetic energy per unit mass is half rho u squared. That's got to equal the potential energy, which is rho g h. So so that tells you that u is equal to 2gh square root, and that's about something like 50 meters per second. Which is way, way, way too fast. Okay, so that didn't work too well. So let's try another method. So we say, well, that's idiotic. because we didn't take into account the dissipation. Let's include the dissipation. So the way you include the dissipation is you say, well, what are the Navier-Stokes equations? I'm not going to write them down. I know you know them. So what we're going to balance is the force that comes from the viscosity against the force that comes from gravity. So what we balance is mu d2u by dz squared is equal to g times theta, and z is this axis going up like that. And the viscosity here is the kinematic viscosity, so it's the molecular viscosity over rho, and that is about 10 to the minus 4 meters squared per second for water. Okay, so now we can solve this differential equation. So the boundary conditions are that u is 0 at z equals 0, and the origin of my vertical axis is right here. So this is z equals 0, right at the bottom of the fluid. So, and then at the surface, there's a no flux condition. So I have du by dz equal to 0, and z is equal to d. And so I can solve that, and you're going to get a parabolic profile, which I think is something like this. If I did it right last night. Something like that. And this characteristic speed u naught is g theta d squared over 2 nu. So then you can ask, well, what is this estimate? So let's just put the numbers in. 10 to the minus 4 times squared 10 to the minus 4. So I get something like 10 cubed meters per second, which is also way, way too fast. So that didn't work. Okay, so let's try something else. So let's go and ask ourselves what Newton.
This is the steady state speed.
The steady state speed. Yep. All of this is just steady state. Thanks. Okay, so let's ask ourselves what Newton knew. So what Newton knew was that the drag force, let me call that Fd, is proportional to u squared, not u. So there's some constant of proportionality. So what we're going to calculate is the following. We're going to say that the rate of energy production is equal to the rate of dissipation. In a steady state. And so let's work out the rate of energy production per unit mass. So that's basically like I take the force, I take the speed, divide by the distance over which it is produced. That's proportional to u cubed over d. This is a famous formula from Kolmogorov, and we'll write this as c times u cubed over d, where c is a constant of order 1, supposedly a universal constant. That's the dissipation. Now let's work out the rate of energy production. This one requires a little bit more thinking about. So the rate of energy production is basically a force and a velocity which is this force, the gravitational force times the time of the angle, the slope, and times the velocity u. And so what I get then is I equate u cubed over d with g alpha u up to constants of order unity. And so what I get is u scale is proportional to the square root of g alpha d. And this gives me 10 times 10 to the minus 4 times 10 is about 10 to the minus 2 meters per second. And so what that says is that in this number, so this is about 1 to 10 centimeters per second, this is about U turbulence is basically of order of magnitude of U experiment for a big river. So what we've learned from this is if you want to understand why a river is flowing or why the air is moving around, the main thing that controls its speed, not the fluctuations, but the speed, the mean speed is turbulent drag. It's not anything else that you may have thought. Okay, so now let's talk about, I should really put this up here, shouldn't I? Does this go up? No. Okay, so that's the first thing. Any questions about that before we move on to the next topic? Yes, at the back. So it should end up being u squared over a length, u cubed over a length. I'm trying to work out the rate of energy dissipation.
Okay, so the road rate.
Yes.
We want to end up with a power there.
This power is right. It comes from the drag times the. Well, what's the problem?
Force divided by time.
Oh, I see. I see. So no. Well, there is a constant here. You're right. There's a dimension for constant that turns us into units of energy per unit time. That's correct. Yeah. But the way I get this is by looking at how much fluid is being moved and how much is dissipated. So that's where this estimate comes from. So this is a constant that does have dimensions. I think that's right. Okay, so that may be confusing and maybe something to look at afterwards. Okay, yes, sir.
Maybe I missed it, but what is R by theta?
What is what? Alpha is the slope of the angle theta. I call it theta. You didn't miss it. I think in the river literature, people use the symbol alpha rather than theta. So that's why I wrote down alpha. I was thinking of that. Yeah, I mistyped it in my notes, and that's why I transferred it. Thanks. Okay, one more question, then I want to move on to the next topic. Say it again.
The value of viscosity.
Oh, I got the wrong number. Yeah, I have, haven't I? Thanks. So homework exercise, correct the estimates. But you're right. You're right, because I made a mistake in converting from centimeters to meters. Thank you. So what was the right number? 6. Yeah. Because it's meters squared. Thank you. Okay, well, I have to see if that changes my calculation. Actually, I think it's still directionally correct. Anyway, the point is, it doesn't depend on the viscosity. And the other estimates are all way too fast. So the point is that the drag is much higher because of the turbulence. So sorry about those mistakes. Thanks very much for spotting them. Okay, so I'm going to move on then. So let's, this is a calculation I'm going to need several blackboards.
Tonight, but while you're erasing that, one question, right?
Yeah,
So it doesn't depend on the viscosity for a river, but of course it does depend on the viscosity in like a capillary tube. So you have, there's some scale transitions in the problems you're thinking about
yes.
that are, related to where on that diagram it's set. So how, how does one get started into thinking about that?
Well, the question is, if I was making fluid go through a capillary tube, the viscosity definitely would depend, the drag would depend on the viscosity.
Yeah.
So there is a transition as you go, increase the Reynolds number, which you can do by speed or viscosity or whatever, where you go into, that regime. The flow through a capillary tube is very, very small Reynolds number. So you're in the the Stokes regime. So in a pipe, we know where that transition occurs. It's Reynolds number 2000, 2038 to be precise. Okay, did I answer your question?
That's exactly my question.
Okay, great. All right. So I talked about the suppression of turbulence. So I'm going to not write notes down about that. So now what I want to ask is, section 3, I want to talk about the propagation of turbulence. I'm going to be thinking about an experimental setup where, for example, I have a system, space, here's some fluid. On this side, there's turbulence. This side is laminar. Maybe the drag has been reduced by suspension or something like this. And we're going to ask, let's suppose we start this off at t equals 0, like this. Then the question is, what happens a long time? So that's the question. Now, what you might guess is, you might say, well, okay, well, we know what's going to happen. Turbulence is some kind of random flow. If you've got a random flow, what's going to happen is if I plotted the turbulent kinetic energy, which I'm going to call Q. So I'm going to put some averages around that. So I'm doing some course grading in space and time. But I'm not going to specify precisely what I mean by that. What you might think of is I start off with some distribution that looks like this, and then gradually what you'd say is, well, this thing is going to diffuse out like so, and then a long time it's going to diffuse like so, and so I'm going to get some turbulent energy diffusion. So you start off with some sort of Gaussian or step function, and it's gradually going to diffuse out. The peak intensity is going to go down, and the turbulence is going to spread. And so that's what you would expect, be a reasonable thing. But then the thing you have to remember is that we're going to specify that here, Reynolds number is very large. And because the Reynolds number is very large, the flow is going to be dominated by K41 Kolmogorov 41 type of physics. And so what we're going to ask then is the following questions. What controls the spread turbulence into the laminar region? And what is the nature of the boundary between them? And we're going to ask, how fast does it spread? So, important point. We're starting off with turbulence, then we're turning off whatever made the turbulence, and then we're just watching it spread and die away. Okay, and this the calculation I'm going to show you, the references to this is work by Grisha Barenblatt, and the papers will be is made available to you, and then my own work with one of my students, Lin Chan. Okay, so so what we're going to find is that there's a lot of surprises in this problem. Okay, so let's set up the problem. So I'm going to have the turbulent kinetic energy density is going to be a function of space and time, and this axis here is going to be the z-axis in my notes. So what we're going to ask then is, what is dq by dt? And we're first of all going to ask what happens if there is no spatial variation. So the answer to this is that this is the rate of energy lost, dissipation, and that's going to go like u cubed over some characteristic scale times a constant like this epsilon naught. This is the calculation that I had over there where I didn't explain that there's a dimensional constant that comes in here like this. So this tells you that this goes like this, and because the kinetic energy is proportional to u squared, I can write this as epsilon naught u to the 3/2 over L. Okay, so now let's put in spatial variation. If I add space, what I would say is this now becomes a partial derivative. I have q3/2 over L over here, and now I'm going to have diffusion. So the diffusion is the divergence of a current, and the current is some energy diffusion coefficient times the flux of energy, which I can write as dq by dz. So that's how I would write down this problem as a differential equation. And this is the energy diffusion coefficient. Okay, so that's an equation, a nonlinear equation, but what Kolmogorov realized was that we can estimate how this works from K41, or rather K42. And his argument was this. This energy diffusion coefficient, normally there's a connection between diffusion and drag. So you might say that the diffusion coefficient should depend on the viscosity. But we are in a situation where we have turbulent flow at high Reynolds numbers. So what that means is that if I want to ask, does the diffusion coefficient depend on nu? The answer is no, it can't. So what does it depend on? So if we want to figure out what it does depend on, we have to do some dimensional analysis. So it's got to depend on something. The only thing it can depend on is Q and L. So if you go and work out what it depends on, it has to be the following, that D is some constant of order unity times L times the square root of Q by dimensional analysis. And you can go ahead and check that. And so we're going to just ignore the constant, of course, and set it equal to 1. And so now we're going to ask the following question. I start off with my patch of turbulence. Over here, that patch is spreading. We'll see it is covering a regime in the Z direction, which we'll call H of T. And what we're going to say then is that the scale that comes in here, this L, I didn't say much about it so far, but this L is really supposed to be something like the integral scale. So the integral scale for an expanding region of turbulence into a laminar is going to be proportional to the size of the region that is occupied. And how this is defined will become clear in a minute. Okay, so we're going to say that L is proportional to H. H will be a function of T. So we'll say that L is equal to alpha times H of T. Okay, so now we're going to write down the full specification of the equation of the problem. So we're going to have dq by dt is equal to alpha d by dz H of T q to the 1/2 dq by dz minus epsilon naught q to the 3/2 over alpha H of T, and this is valid when Z is in the region occupied by the turbulence, and we're going to, and it'll turn out that Q is 0 for Z greater than this. So the reason that I can write it down like this is because once I know that the turbulent energy depends on the square root of Q, this problem is now nonlinear. And we know, and you'll see this in the papers I will show you, that once you have a nonlinearity coming in here, you no longer have a diffusive tail that you would normally get in a diffusion process. This equation can be mapped into something called a porous medium equation, and we understand the properties of that very well. And in fact, how this, if you have an exponent n over here, and you send n to 0, how this maps into the Gaussian is a really beautiful piece of mathematics that I'm not going to show you. Okay, let's suppose that the initial conditions are that Q of Z and 0 is some number contained within an initial size A, some functional form Z over A, where Q is the total energy contained in the turbulent region between minus A and plus A. And therefore, by the way I constructed this, the integral from -1 to +1 of this function u naught is just equal to unity. That's a specification of the problem. Okay, very complicated problem. Okay, the amazing thing is that you can solve it. Okay, so what I'm going to do is we're going to first of all look at part. And we can solve this part exactly. I'm not going to show you how I get the solution for that, because it would take me too long. But I'll show you what it is and you can verify it. And this goes back to work that was done by Barenblatt and Companies in 1952. Showed how to solve this. It's much simpler than it looks. Okay, so that's the first thing we're going to do. That's the first part of our strategy. The second thing is this part over here, we're going to add as a perturbation. So we're going to make it as a perturbation to this exact solution. And if you do this formally, what you find is that when you add this perturbation, the solution has divergences. And I'm not going to go into the mathematics of those divergences. They're in my paper from a long time ago. But I'll show you how we can solve this using very simple physical arguments of adiabaticity. And we can solve this problem with this as a perturbation. And what we're going to see is that we get a diffusion process, but it's a super diffusion. And we can calculate it, and it has anomalous dimensions as well. Yes?
So what's the definition of small h?
H is the size of the turbulent region. So this is laminar. This is turbulence. And this part of the fluid here is becoming turbulent as the turbulent to laminar transition occurs, as this spreads, and then also the turbulence itself is spreading over through the whole system. Okay? All right, so let me tell you what is the exact solution to this problem.
H of t is given.
H of t,
Given in terms of Q.
no, H of t is something that we're going to have to find.
Okay.
This is
I
a
only see one equation.
this is a moving, so this is a moving boundary problem. And so the solution to the moving boundary comes from the equation itself. So we're solving an equation for Q. At the boundary, the turbulent intensity is 0 by definition. We'll see that it is. You don't know that ahead of time, but you can check that that's the case. And so we find the size of the domain in which we are solving the differential equation as we solve the differential equation. That's why this problem is horrifically nonlinear. All moving boundary problems are like general relativity. That's correct. Yep. So it's sharp. The reason it's sharp is because of this term over here, which you can't really see. It was something, yes. It's not obvious. So you have to just do dimensional analysis and ask how it should scale if I'm using K41 idea, which is that I'm not allowed to use nu, the viscosity, the kinematic viscosity, in my dimensional analysis. So it literally, I don't know if you can see it from where you're sitting, it just comes from the dimensional analysis. So you can check that, okay?
Here's a characteristic velocity, right?
Yes.
Some sort of turbulent characteristic.
Yes. Okay, so here's the solution. Let's set epsilon equal to 0 and find out what the solution is. And the solution is this. There's a solution, okay? So really the way you solve this is by making a change of variables, substituting, doing separation of variables, turning it into an ordinary differential equation and solving it. It's very simple to solve. So, I'm not going to spend class time to do this, but it's not as bad as it looks. This symbol here what that means is when I write f of z plus, what that means is it's equal to f of z, and f is positive, 0 otherwise. That's what we mean by this symbol. So
You've chosen some particular U0 if you over A, like a step. Or is it already a parabola?
it comes in into the Q. Yes, in this one here, I chose it to be a parabola. Yes, that's right. Thank you. This quantity psi naught is 135 alpha squared over 4, and h of t is equal to psi naught 2/3 q to the 1/2 t plus the initial size of 3/2 all to the power 2/3. Okay, so that is the solution. And what you can see is that as to infinity, this thing goes as t to the 2/3. Okay, and so that's the solution. So what that looks like, if I plot this function, here is z, here is q. It looks like this. And this thing here is h of t, and this is going out as t to the 2/3, not t to the 1/2, as you would guess if you had diffusion. Okay, so this is not that hard to do, but I have to, of course, I'm not going to say that it's trivial. So now let's ask what happens when we now include the effect of turbulent dissipation. So let's, ow! Let me do that. Okay. All right, so now let's put epsilon on 0, and let's make it very small. Okay, so the idea is that energy is no longer conserved. So you say, wait, why was energy conserved in the first place? Well, if I take the equation up here and I set epsilon naught equal to 0, you can check, you can see that this is just a conservation. So it has it, so the integral of Q is always conserved. The energy just gets spread out. But now we've got this turbulent dissipation, so energy is being taken away from the system. So energy is no longer conserved. So what we're going to assume is that the removal due to turbulent dissipation is slow with regard with respect to the spreading rate. So you can imagine that the turbulence spreads a little bit, then you take some of the energy out, then it spreads a bit more, you take the energy out, spreads a bit more, you take the energy out. But the main point about this is that this is slow, and so because this is slow, this is an adiabatic process. There's a separation of timescales that I'm assuming for this limit, and what that means is the adiabatic means that my form of Q, Z and T, when I have epsilon non-zero, is the same functional form, Q, Z and T, when epsilon is non-zero, but Q, the total energy, is now replaced by a Q of T. So this is the time-dependent total energy. So what I have to do then is I take my formula over here and I look everywhere where Q occurs. So where does Q occur? Well, Q occurs here. So this now becomes a Q of T. And then Q occurs in here. because it occurs in here. So I'm going to make that time dependent. Okay, so how do I know what the time dependence is for Q? So what we're going to do is we're going to calculate that. And the way we're going to calculate it is we're going to write down we're going to write down an equation for Q of T. Sure.
Is there some notion of universality in this quadratic shape? Is that an asymptotic universal?
Yes, it will turn out that this is a similarity solution, or a type 2 intermediate asymptotic similarity solution, and so it's a long time attractor. But I'm going to just make the calculation simple. To calculate it, we're just going to assume we start off with a parabolic profile, but the long times, irrespective of what I started off with, it will attend asymptotically to that profile. Yeah. Okay. So how do we get an equation for Q of T? Well, we know what Q of T is. Q is defined as the integral from minus h of t to plus h of t, Q of t dz. That's what we mean by Q of t. So then, if I want to take its time derivative, I just stick a d by dt in front of here, and I stick a d by dt in front of here. And now what I'm going to do is I'm going to use the term use for Q, this function Q naught is zt Q of t. So first term is not going to give you anything, and the second term is going to give you this. So I get dq by dt is equal to minus epsilon alpha h of t, the integral from minus h to plus h of q to 3/2 dz, just from the full equation. Okay, so let's work this out. So this q of z is equal to q t xi naught cubed over 6 alpha cubed h of t minus z squared over h of t squared plus squared. So now I just have to substitute this functional form into here. I take this equation, that's my ansatz, and I plug that into here, and what I get is this. dq by dt is equal to minus epsilon over alpha q to 3/2 over 6 alpha cubed xi naught 9/2 h to 3/2, the integral from -1 to +1 of 1 minus z squared cubed dz. Okay, and you can just do that integral. Now, what happens for this? What we're interested in is the long time behavior. So for long times, what we know, let's go over here. So keep that equation in your mind. Let's write down so for long times, my function h of t goes like psi naught times q of t times time to the 2/3. So that means that h to the 3/2 goes like psi naught to 3/2 times the 1/2 times time. So my equation for dq by dt is equal to minus some stuff, you can read off from there, times q over t. And it's important, all the factors of q turn into, cancel out, and I just get one power law left. dq by dt is q over t times stuff. This is an equation that you learned to solve on your mother's knee, because this says dq over q is dt over t, which means that log of q equals stuff times log of t, which means that q goes as a power law. This is the miracle of this. You get a power law behavior of q. And so what you get is, if I write down the full solution, q of t is equal to q at some initial time t naught times t over t naught to the power minus epsilon over 7 alpha squared. And so what that tells me then, if I put all these things together, is that now my full solution goes not as t to the 2/3. It tells me that my full solution now is modified by this power law. And so I get an anomalous scaling. So let's put it all together. So h of t scales like q to the 1, q of t to the 1/3 times t to the 2/3, but q of t itself depends in this power law way on time like this. And so what I've now shown you is that the size of the turbulent region scales as t for large times as t to the 2/3 minus epsilon over 21 alpha squared plus order epsilon squared. And this behavior here is what is known as anomalous scaling. And this correction here can be made more precise if you do a renormalization group calculation whose physics is identical to what we just talked about. We get this result. Okay, so that's an RG calculation done on a partial differential equation. There's no noise, no thermal fluctuations, no integrating out degrees of freedom. Everything that you may have learned about the normalization group in your graduate statistical mechanics class was completely irrelevant to the calculation I did. There's a lot more that one can say about this, but I don't want to do that now. So let me now. The physical significance of which?
Ratio epsilon of alpha squared. You can understand what properties of turbulence in those numbers.
I don't know. Okay. I don't. I mean,
it's not the epsilon over alpha.
Yeah.
Yeah. Okay.
Yeah. I don't. I other than what I just told you, is the simplest form I can tell you.
Yeah.
I don't know how to. I mean, alpha is just a number. It's just a constant of proportionality. Okay. So I don't think it has any real significance. It's just 3. Okay. The important thing is it depends on this epsilon naught. So it shows you that the turbulent energy dissipation makes a correction to the power laws that you get here a long time. Okay. So here's the cool thing. You can do this experimentally. Okay. So let me end by telling you a little bit about the experiment. I'm not going to say very much about it. Now, we can't really do the experiment accurately enough to test this prediction. But we can test that there is a sharp front and that it spreads as a power law close to 2/3. Okay, and so most of this work was unpublished, but I'll tell you the results of it. Okay, so let me show you how this was. No, please don't name anything after me. But the first calculation for that was done in our paper in 1992 using a full RG calculation. And if you want to learn about how you do a normalization group for differential equations, which certainly is relevant to what we're going to talk about in the next two lectures, my early papers in the 90s showing you how to do this are worth reading. And they also make contact with things that you may have learned about in graduate numerical field theory, things like the Callan-Zemantic equation, Gelman-Low RG, and so on. So let's just end by just telling you how do we see this experimentally. So this was done numerically. This calculation I just showed you was done numerically by Barenblatt in the 1980s sometime, and then done by RG by us 10 years later. Okay, the sharp front is what's predicted. We're trying to look at the spatial patterning of a problem that we don't understand, turbulence. So it's remarkable that you can get these predictions based on very simple scaling arguments. So this is a generic prediction, and now let's talk about the experimental observation. Okay, the experimental observation was work that I did with Mike Smith, late Russ Donnelly, me, and we did this in superfluid helium in about 1993 to 1995. I think you heard about some of these things from Srinivasan, from Professor Srinivasan. He talked about quantum turbulence and its decay. I think he showed you the T⁻³ decay law for the vorticity in quantum turbulence, which was a result that I first worked out in 1992 in these experiments. Some of the papers on this, there was a physical review letter that was on the uniform decay of turbulence. And then the unpublished work is the spatial part, which was published in the conference proceedings later. And we never wrote the full paper because Russ Donnelly wanted to get better accuracy, and then people left, and then later Russ Donnelly died, and so we never finished the work. Okay, so here's the experiment, and it's a really beautiful experiment. So what you do is you take a pipe and you put in it helium-2. Just a different color than water. Okay, what you do is you create turbulence by getting a grid, and you pull the grid through the pipe, like over here. And the idea of pulling the grid is that you then create some turbulence in this superfluid. So this is at temperature about 1.6 K. And now we're going to watch the turbulent laminar transition in this system. How do we watch it? Well, the only thing you can detect in superfluid helium are quantum vortex lines. And you detect them by the attenuation of second sound. Second sound is a temperature or entropy wave that happens in superfluid helium. And I'm sure you heard about that from Srinivasan. So what you do is you create a second sound standing wave over here. So this is a second sound standing wave. And actually, I think what we used was something like the 40th harmonic, something like that. And so now we're going to make it a guess. We're going to make a guess. I told you that theoretical physics is all about guess. So we had a guess, and we guessed the following: that in the superfluid you have the superfluid velocity, and you have the normal fluid velocity. And our guess was that in turbulence, Vs and Vn get coupled together. And the reason they get coupled together is because of quantum vortex waves. So second sound is a temperature wave. Temperature is just phonons, thermal excitations. So your picture of a box of superfluid helium is that I have in this box a quantum vortex line. The other thing, that's a topological defect. The other thing that you have in here are phonons. And so that what happens is that the phonons, they can scatter off the cores of the quantum vortex lines. When they do that, they're going to transfer momentum between the normal and the superfluid component. So in the classical literature on superfluidity, these things are meant to be independent, meaning that they don't transfer momentum. When you have quantum vortex lines, you have a mechanism for quasi-particles to bounce off the normal cores and transfer momentum between them. So our idea was that in that case, what's going to happen is that the quantum vortex lines will track the vorticity in the normal fluid. Yeah, I said it to give me 15 minutes warning. Last time, yeah. I'm going to leave this as the last thing. So the idea then is that what we expect is that when I'm measuring the vortex lines, what I'm actually getting is the vorticity of a classical fluid. So what's going to happen then? So basically what we're saying is that once I've created turbulence here by drawing this grid, I've got turbulence in both the normal component and the superfluid component. So this turbulence is going to spread out like this. And what I'm going to measure, my readout over here, is I measure the attenuation of the standing wave. When I measure the attenuation? Well, once I have a quantum vortex line in there, it interferes with a wave of heat, the wave of phonons. And so it damps it. So if I measure the Q factor of that resonance, that Q factor of the resonance tells me about the quantum vortex line density, and therefore tells me about the vorticity in the normal fluid. Okay, so what do we expect to see? what's going to happen is that this turbulence is going to spread along here if the theory is correct. And that means that if I measure the attenuation, I'm going to see there's no attenuation until the turbulent gets to the second sound standing wave. So I'm going to plot along here time, and here I'm going to measure the attenuation in the Q factor of the second sound standing wave. And so what's going to happen is if the theory is correct, I would expect this. Nothing happens. There's no attenuation until eventually this spreading turbulence gets out to here, gets out to here, gets out to here, and then bang, it crosses this and suddenly causes attenuation. So I can work out from the solution of the spreading, I can work out what should be the shape of this function. And it should go like this, then there should be a large jump, and then it should decay eventually like this. And so what's happening in this picture is that over here, it's laminar. Until over here, the turbulence arrives, and then decays away. And of course, you can vary how far away your detector is from your initial turbulence. So this L can be varied. And that means that you can do time of flight measurements. So from that, you can work out, you can then measure what h of t is. And so this result here, this here is because I have a sharp front. If I had some just regular diffusion of turbulence, what I would see is something like this. And you don't see that. You see this sharp front. So Russ Donnelly was very excited by this. We published some of this. We wanted to do the experiments in water and so on, but unfortunately, he passed away before we could really finish that. Okay, so what is the...
Any sign of that onset there, or is that sort of buried in the experimental
No,
knowledge?
we can't see anything like that. The data really look like this. It's really sharp, and you can fit because you know what the dissipation is in terms of vorticity for homogeneous isotropic turbulence. Epsilon goes as nu omega squared. You know how to relate omega to Q. So from the solution for Q, we can work out exactly what this function should look like in time. And it fits very well with what you see in the data. So it's a real shame that we never published this. It's just staggering. I mean, there's a conference proceedings, there's a thesis of my student. It's really quite beautiful, I think. So let me just say what the conclusion is. So what I've told you today are several things. I've told you that laminar turbulence transitions occur in many ways. In space or time, through suppression of turbulence, through propagation of fronts. I've shown you, well, I haven't yet told you what we're going to talk about next time. Well, what I've told you is that we can make predictions. We can predict qualitative phenomena at high Reynolds number. And just using Kolmogov's simple scaling arguments. And the next topic that we're going to talk about is transition to turbulence, to or from turbulence, as you vary a parameter. Such as Reynolds number, Rayleigh number, and so on and so forth. And that will be the topic of lectures 2 and 3. Okay, I'll be happy to take any questions.
Thank you. Thanks for question.
So throughout this analysis, one of the important assumptions was that perturbation was weak. And
Yes.
That, the dissipation was slow.
Yes.
So I was kind of.
Is it true?
Yeah. Is it true? And then how is it related to some of the previous lectures talked about the energy cascade being local? This assumption about being local. Basically, is it essentially the same kind of assumption?
Yes. Thank you. Thanks for the question. Good question. So first of all, of course, all we can do is perturbation theory because that's all we know how to do. And even that's hard enough. Okay, what I showed you was a sort of 3-line argument, which is like several pages of physical review and lots of nasty calculations, but they're interesting ones. Okay, so yes, if you then solve these equations numerically and you see how good this renormalization group improved perturbation theory is, the answer is it's very good. Okay, this is a characteristic thing. So one of the things that we did many years ago, and it's sort of in textbooks and things like this, is using renormalization group to solve any singular perturbation theory problem, any asymptotics problem you like. Okay, there's methods that you may have heard about in these lectures, like matched asymptotic expansions and boundary layer theory, WKB, multiple scales analysis. All of those things are special cases of the normalization group. And what the normalization group does, and it's not the topic of my lectures, but what the magic is that it not only gives you solutions that are very singular in ways that you can't get other ways, it's also very systematic and it's also robust. If you do a perturbation theory calculation to order epsilon, then you improve it by renormalization group, the resulting improvement is valid for epsilon of order unity. So the technical thing that I pulled the wool, I really pulled the wool over your eyes, like many times here. Okay, if you do this calculation but using perturbation theory, you find that the perturbation theory diverges. You cannot do a perturbation theory of this problem. And the reason is because, how do you make that thing go down? This term here, Q to the 3/2 of H, has the same dimensions as this term over here. So it's what you would call in the normalization group, if you did a perturbation theory about this first term, this has the same dimensions. So it's a marginal perturbation. Okay, so as you know, when you have marginal perturbations in the normalization group, you don't have universality. The critical exponents depend on the coupling constants. Over here, our critical exponents, which tells you how fast this thing is going, depends on epsilon and alpha. Okay, so we use that fact, we exploit that marginality to get those results. So the bare perturbation theory just gives you a perturbation theory that's useless. When you use Gell-Mann-Low RG to improve it, then you get a form that is very stable even for large values of epsilon. Okay, second question you asked about the locality of momentum space, the cascade. That really is buried in the assumptions of K41 that we used in constructing this theory. Because the way that came in was we worked out what was the functional form of the energy diffusion coefficient. And to do that, we used Kolmogorov scaling, which said, nah, forget about viscosity, it doesn't matter. That says I've got a high Reynolds number, so I've got a large inertial range, and energy is being transferred scale by scale through the cascade. So that's where that comes from. Does that answer your question? Okay. I'm so sorry. There's one question over here.
Professor, I have a question. If we consider a long time behavior, then I guess the Q becomes smaller and smaller.
Yes.
So will there be at a point where it transitions back
Yes.
to numerical?
Thank you. Yes. So the question was, well, eventually the turbulent energy is lost. So much is lost that the Reynolds number goes from being high to being of order unity. And at that point, then it becomes dissipative in the standard way, and you get a full transition to laminar flow. That's exactly right. So this is an intermediate asymptotic range where T is large enough that you can see the asymptotics of the turbulence, but still less than the transition to ultimate transition to trivial laminar dissipation.
Let's go ahead. Please, Bob and Nigel with more questions.
Yeah, I'll be here all week and all day, and so please feel free to ask me questions. I'll do my best to answer them.